All right, so we're going again. Here we go. Let's take a look at the next slide. And the cursor's not working, so... All right, so another thing that I want... So you guys understand what relative density is, right? Okay, the second thing... You guys understand what mass is first. So make sure you understand what mass is and how it differentiates from weight on Earth. Okay? Second thing, make sure you understand what relative density is as a concept. Okay? Now, let's talk about conductors and insulators. All right? You guys have probably heard both of these terms. You guys know that wires are used because they're good conductors. And you guys know that the outside of the wire in electrical wiring usually has a plastic coating that's an insulator. Okay? You guys know that walls have insulation. So, substances that readily transfer heat energy, quickly, easily, really, really efficiently, are called conductors. Typically, they are denser, and most of the time, in our particular situations, we're going to think of them as metals. Although there are other things that are decent conductors that are not metal. Okay? And I'm talking in very simple terms here. Science always throws a curve at you. The world and our universe throws a curve at us constantly. So we're not talking about what happens to matter when it approaches absolute zero. We're not talking about superconductors or any of that stuff. We're talking about really simple, dumb, average terms. Think of it of what I don't know, a 7th or 8th grader might understand. Okay? Okay. Substances that do not readily transfer heat energy, or electrical energy for that matter, are called insulators. They are typically less dense, okay? And the material, the heat energy and electrical energy does not travel through them very well. So plastics and woods are good because they're a lot less dense than, say, metal, okay, as being an insulator. So here, you've got to understand what is a conductor, what is an insulator, in general, simple terms, okay? All right, the next topic that we need to kind of understand in order to understand how energy moves is something called specific heat. Specific heat and its relative specific heat content are very, very closely related. But specific heat is going to be the amount of heat energy, okay? It's going to be a value, actually. Specific heat is a value that is assigned to different substances. And it's typically going to be the amount of heat energy that will take a given substance and raise its temperature by 1 degree. Okay? Well, it's right here. Specific heat is the value assigned to an object that tells how much heat energy it takes to raise or lower its temperature by a certain amount, typically 1 degree. Beware, right? Them scientists, gosh darn them, they measure stuff in joules. And those aren't family joules, they're joules. Right? And they measure stuff in grams and kilos. They're all must be into drugs or something, I don't know. At any rate, so it can get confusing. Us archaic people in the United States, we measure stuff in British thermal units, and we measure stuff in pounds. So it all gets kind of confusing. So specific heat can be used to compare, right, how much heat a given object can hold. So a piece of styrofoam can hold a lot less heat than a block of concrete the same size. Okay? So let's use the example of liquid water, because that is the standard, right? Before they came up with the idea of joules and kilos and all that stuff, I believe that they had already come up with this notion of the British thermal unit. And the British thermal unit was the amount of energy that it would take to raise 1 pound of water by 1 degree Fahrenheit, not Celsius. That's another confusing issue. All right, so now let's take a look at specific heat capacity. So specific heat capacity is the actual ability of an object to store a quantifiable amount of heat. Okay? So using the earlier example, we talked about copper and relative density, right? So what was the approximate weight of, what was the approximate density of water compared to copper? Per cubic foot, right? Versus 500 and something, 590 something or whatever. All right, so the specific heat capacity of water is 1 BTU. So it requires 1 British thermal unit of energy. Now think back to what I told you guys heat energy was. Remember I put up that little bar and it had little flame guys sort of next to it vibrating the molecules? So whatever it takes to be 1 BTU is a certain number of those little flame dudes shaking molecules. Okay? So it's applied to 1 heat of water and it raises it by 1 degree Fahrenheit. Okay? So the specific heat of water is 1 BTU per pound per degree. The specific heat of copper, on the other hand, is 0.09. So that is tiny compared to that, right? Per pound per degree Fahrenheit. All right? Don't get too caught up on the math. Just try to think about the units. If we convert it to SI units, 1 kilo of water will require 4,184 joules of heat energy to raise it 1 degree Celsius. And it gets really tricky doing the conversion between these because not only is this different, but this is different and this is different. So all 3 scales are completely different, but they really measure the same thing. Now comparing joules to comparing water to copper, copper uses 385 joules per kilo per degree Celsius. Now you might not be able to do the conversion, but you could probably do a simple ratio and you would find that the ratio of this to this is probably about the same as this to this. Okay? So, all right, in either case, when you look at this, the given amount of water can hold 10 times more energy, more heat energy, than the same piece of copper. Okay? And it's a little bit more, but so what's 10 times 385? 3,850, right? Is that kind of close to that? Okay, I'm talking order of magnitude. So fine, somebody get a calculator out. Get a calculator out and take 11 times 385. So what's 11 times 385? Oh, so now it's more, right? Okay, so it must be somewhere between 10 and 11, right? Maybe 10.9 or 10.8. That's the point I'm trying to make. So, and if you do this one, you'll see that it's the same. Okay? All right, direction of heat movement. This is important, okay? And it seems really simple, but you guys got to understand that it's happening right now, all around you, in every single thing that you are looking at in this room, including this projector, okay? The direction of heat energy always moves from a higher state, which is hotter or warmer, to a lower state, which is cooler, okay? So always, if something's hotter and something's cooler, the energy is flowing towards the cooler side. So let's take a look at a couple of objects. So you all drink coffee or tea or something hot? Yeah? Okay. So what happens when you buy a cup of coffee or tea and you set it on the table and you forget it?
It gets cold.
Yeah, and then, a little bit later you go take a sip and you go, oh, yeah, that tastes terrible. Jeremy, how many minutes am I at? Oh, I got it, 9 minutes. Okay, so where did the energy go? The energy went a certain direction, right? Okay, look at the opposite. How many of you guys have ever had a cup of ice, a nice frosty cold soda? Like a Coca-Cola without rum in it. Okay, and a lime. That would make it a Cuba Libre. Right? But eventually the ice melts, right? And eventually the soda warms up to room temperature. So one went from a higher state to room temperature. The other one went from a colder state up to room temperature. Okay? So in the case of the previously mentioned coffee, the heat was transferred from the cup, or the material, into the air around it. Okay? Because air has temperature, right? You guys have walked into your houses probably this week, and if the heater was off, the air was cold inside of it, right? Likewise, if the heater was running and you went out for a run or a walk and you came back in, now you're like, oh man, it's hot in here. It's stuffy. That happens at my house all the time. You get up and you're freezing your tail off, and you go for a walk, take the dog to go do its duties, and come back and, oh, it's hot in here. So, all right. Again, I want to make sure you guys understand. These are super simplified. I'm ignoring the table. I'm ignoring what kind of container the thing is in, how dense it is, what its emissivity is, which we'll talk about that shortly. All right? So it's just simple terms, right? It mostly got transferred into the air around it. All right, temperature differential. Temperature differential is known as delta T, okay? That's a common engineering and it's a term that architects will be sort of familiar with. Delta T means temperature differential. If you have two things that are at different temperatures, there's a delta T associated with it. And the delta T, as an example given here, is if it's 70 degrees inside of this building and it is 50 degrees outside, the delta T is 20. Now note that delta T is not directional. It just tells what the differential is. You have to think about what direction it's flowing, but it's just, hey, there's a differential and heat's going to move. Okay? The bigger the delta T, I got it. The bigger the delta T, okay, the faster that heat energy moves. Imagine those little heat dudes, right? And they're in a bar of metal and it's really hot. So they're all dancing around, shaking, woo, right? And then all of a sudden you take that hot bar of metal and you drop it in a bucket of water. The delta T between the water, right, and the bar of metal were substantial. And so the energy moved really fast. Right? The cup of coffee in the room, on the other hand, the delta T between the air temperature and the coffee wasn't anywhere near as great, and so it didn't move as fast. The greater the delta T, the faster the heat moves. Okay? One more term that I want you guys to be aware of is that when two things reach the same approximate temperature, they are said to be in thermal equilibrium. Okay? So now let's take a look at methods of heat transfer. There's three methods of heat transfer. You guys have probably heard this in high school. Conduction, convection, and radiation. Conduction is the movement, okay, of heat particles at the molecular level in a solid substance. And it usually takes the place of some heat thing vibrating and moving it across. Actually, you know what? I'm going to stop here and I'm going to move on because it's going to get too long. So I'll revisit this one in the next video.